Hello everyone, my name is Hyung-Seok, and today I would like to present my work on an immersed phase field model for fracture-induced Stokes-Darcy flow. The target material of this study is a VUGgy porous media. A VUG is an orifice in a porous medium that is relatively large compared to the pore size of the matrix and is often observed in carbonate rocks such as limestone or dolostone. Modeling fluid flow inside this medium requires coupling of free and porous medium flows, which has been not only used to model geological materials, but also has been used in biomechanics field to model blood vessel system or respiratory system. A model that simulates coupled hydromechanics in VUGgy porous media is called BuildStokes model. It adopts the Stokes equation to model the free fluid while uses Bio's pore mechanics theory for the intact porous matrix. This BuildStokes model is the starting point of this study. Consider a body that consists of BD, the intact porous matrix, BS, the free flow region, and the sharp interface gamma star between the two regions. We assume that solid constituents form a skeletal structure in BD, while we assume that the solid is completely liquefied in BS. The governing equations for the region BD looks like this, which adopts the effective stress principle to capture the hydromechanically coupled behavior, while the porous medium flow is modeled by the Darcy's law, where velocity WFD and the gradient of pore pressure PFD has a linear relationship. On the other hand, the flow inside BS is governed by the Stokes equation, where this sigma Fs indicates the fluid stress that depends on the pressure PFS and the velocity WFS. As shown here, we also assume that liquefied solid follows the same constitutive relationship as the free fluid, while we adopt the concept of effective viscosity that depends on the particle concentration C in order to replicate the suspension flow in BS. The Stokes and Darcy flows can properly be coupled along the interface by enforcing three transmissibility conditions like this. The first constraint is the fluid flow continuity, the second one is the normal force equilibrium, and the third one is the Beavers-Joseph-Safman condition that balances tangential forces by considering the friction at the interface. Here, this parameter alpha SD is the frictional coefficient that describes the roughness of the interface. This coupled flow can be implemented by using two numerical subdomains and combining them together with the transmissibility conditions. However, the implementation becomes extremely difficult when this interface is evolving. Therefore, the goal of this study is to propose a model that is capable of handling the evolving interface. In order to resolve this issue, this study adopts diffuse approximation of the sharp interface by using the phase field. By generalizing the phase field as an indicator of defects, we consider vugs or cracks as a completely damaged region, while the intact porous matrix as an undamaged region. We also consider the evolution of the interface as a brittle fracture, so that the governing equation for the phase field looks like this. It should be noted that the phase field itself can be regarded as a smooth approximation of the Heaviside function, and its gradient can be regarded as an approximation of direct delta function. This approach basically enables us to transform all the subdomain integrals into volume integration over the entire domain that appears in the weak form, and also the surface integrals along the interface can be transformed into a volume integrals by using the phase field. By using the standard weighted residual procedure, the weak form of the governing field equations and the interface conditions can be expressed like this. From this weak form, we derive the immersed phase field BuildStokes model. We first substitute the interface conditions into the governing field equations like this, and then convert the subdomain integrals into the integral over the entire domain by using the smooth interface approximation. From this procedure, we can get the weak statement of the phase field BuildStokes model like this, while the detailed derivation process can be found in our recent paper. We first conduct a numerical example to explore the effect of frictional coefficient. This test case consists of a rigid fluid channel that is intercepted by a porous medium. For the flow in the channel, we prescribed a parabolic flow velocity on the inlet, while the outlet pressure is set to be 0. These figures shows the effect of frictional coefficient on the flow pattern. These arrows indicate fluid velocities, and as you can see, the arrows near the interface that are parallel to the flow path are affected by the frictional coefficient. As frictional coefficient becomes larger, the velocity profile along the line A prime becomes sharper due to the friction at the interface, and as a result, higher pressure builds up inside the domain. We now focus on the evolving interface. The state-of-the-art of modeling hydraulic phase field fracture is to enhance the permeability inside the crack, which is based on the cubic law. As summarized in this table, our new model uses Stokes' equation to model fracture flow, while other models adopt Darcy's law by enhancing the permeability along the crack. Also, while our new model is capable of explicitly modeling the friction at the crack surface, permeability enhancement approach implicitly models it by idealizing fracture as two smooth parallel walls. We compared the difference between two models by solving the boundary value problem that looks like this. We applied tensile loading on the top of the square domain that has an initial notch at the middle. By using the same material parameters, two models yield same fracture patterns, but our model had lower peak stress compared to the permeability enhancement approach. This is because in our new approach, fluid pressure inside the fracture remains low, while higher negative pressure builds up in surrounding Darcy's region compared to the permeability enhancement approach. As illustrated in this figure, this is because the free flow region can be interpreted as a region that has higher permeability, so that the pore fluid tends to flow into the crack faster, which leads to higher effective stress that eventually causes crack to propagate at a relatively lower load level. We also highlight the model capacity by simulating the crack cavity interaction triggered by mechanical loading. As illustrated in this figure, we prepared a domain that has 9 explicitly modeled cavities and its homogenized counterpart, and performed numerical experiments by applying tensile and shear loads respectively. Also, for the homogenized case, we adopted the homogenized properties based on the volume fraction of the cavity theta cav instead of using the material properties of the intact porous matrix. This figure illustrates the evolution of the phase field for both tension and shear tests in a computational domain where the cavities are explicitly modeled compared with the crack trajectories obtained from the homogenized domain. The domain without cavities exhibits the crack patterns that are similar to the results of previous studies on homogeneous solids, while the domain with explicitly modeled cavities exhibit distinct crack patterns. More importantly, the global force displacement curves reveal that neglecting the interface between the cavity and crack and the homogenized model may lead to oversimplified global responses that lack the distinctive characteristics of the crack cavity qualities. For the case where the cavities are explicitly modeled, the porous matrix initially undergoes linear elastic deformation until the crack nucleation takes place. After the first peaks, the crack starts to initiate from the tips of the pre-existing flaws, since they experience higher stress concentration compared to the matrix cavity interface. After the coalescence of the cavity and the crack, the reaction force in both cases increases again, and the crack eventually reaches both ends of the specimens. The figure below shows the snapshots of pressure fields from a domain with explicitly modeled cavities under tensile and shear loadings. In both cases, the leakage of pore fluid takes place towards the interconnected cracks and cavities in the middle. In summary, we proposed a new model which considers hydromechanical coupling effects in BuildStokes system. Also, by extending this model, we were able to propose a new model for brittle fracture in vuggy porous media, which is capable of explicitly modeling the friction at the crack interface. From this study, we aim to extend this model to three-dimensional cases while considering Navier-Stokes Darcy flow with high Reynolds numbers in the future. Thank you so much for listening.